In this example, we want to find the response in terms of omega of the ratio V sub L divided by V sub N. First, we will rename resistors R1, R2, and R3 and the inductor C sub L. Next, we will find an equivalent network by combining the resistors in parallel with C sub L, and we will find the voltage across V sub L. Voltage across V sub L is going to be C equivalent divided by C equivalent plus R sub 1 times V sub N. Since we want to find the ratio V sub L divided by V sub N, this is going to be C equivalent divided by C equivalent plus R sub 1. What is C equivalent? C equivalent is the combination of resistors R2 and R3 in parallel with C sub L. So that C equivalent is equal to C sub L times R2 plus R3 divided by the sum of C sub L plus R2 plus R3. Next, V sub L divided by V sub N is the parallel combination of C sub L times R2 plus R3 divided by the parallel combination of C sub L times R2 plus R3 plus R1. We are going to continue working with our expression, and now we're going to add C sub L plus R2 plus R3 to resistor R sub 1. This will eliminate the expression C sub L plus R2 plus R3 from the numerator, and then we will have in the denominator C sub L times R2 plus R3 plus R1 times C sub L plus R1 times R2 plus R3. Now, substituting the values of L as j omega divided by 2 and the values of the resistor 2 plus 2, then we have the following expression. Continue working with the ratio. We have that numerator is j omega 2 divided by j omega 2 plus j omega plus 2 times 4. So that's going to be j omega 2 divided by j omega 3 plus 8. The next step is to put this in a standard form. Standard form means that we're going to leave the j omega standing alone, and so we have to factor out on the numerator 2, and in the denominator we factor out 3, so the expression is 2 times j omega on top divided by 3 times j omega plus 8 divided by 3. Now we can see that V sub L divided by V sub N is a complex number, and that's a complex number on top and a complex number at the bottom. Every complex number has magnitude and phase. So for the magnitude of V sub L over V sub N, we know that is the square root of the square of the imaginary part, and then on the denominator is 3 times imaginary square plus real square, and that at the end is equal to 2 times omega divided by 3 times the square root of omega squared plus 8 divided by 3 squared. We can see from this expression that we're going to have a 0 at 0, and we're going to have an asymptote at 2/3 when omega goes to plus or minus infinity. For the phase, we know that we will take the arctangent of the numerator and the arctangent of the denominator expression. So the numerator is complex number with 0 real parts, so it's omega divided by 0. The denominator then is imaginary divided by real, omega divided by 8 over 3. If we sketch the magnitude, then we can see that when omega is equal to 0, we have 0, and when omega goes to infinity, this is going to go to an asymptote that is going to be at 2/3. Now, the values for the phase, we have to create a table and then put some values. Let's start with omega equals 0. That means that our phase is going to be 90. Is a plus or minus 90 because at this moment we don't know if at omega equals 0 the numerator is going to go positive or negative. The denominator when omega is equal to 0 will give us angle 0, so that's going to be plus or minus 90. If we move towards the positive values, 8 divided by 3, then we can see that the numerator actually takes on positive numbers, so it's going to be plus 90, and the denominator will be 8 over 3 divided by 8 over 3. The arctangent of 1 is equal to 45, so 90 minus 45 will leave us with 45 degrees. As omega goes to infinity, then we have 90 minus 90, and the angle will go to 0. As we move to the negative values of omega, minus 8 divided by 3 will give us a minus 90 degrees for the numerator, since omega is divided by 0, and the argument of the arctangent is negative, and the denominator will give us a minus 45 because it's minus 1. So minus 90 minus 45 will give us minus 45 degrees. As omega goes to minus infinity, so the numerator will give us minus 90 because the argument of the arctangent is going to be negative, and the denominator will give us also minus 90, and minus 90 will give us 0. So when we sketch this, starting first with the positive values and positive angles, we see that we go from plus 90 to 0 when omega goes to infinity. And if we work on the negative part of the spectrum, for negative values of the variable omega, we get negative angles, and that's how the magnetron phase will look like.